In the name of Almighty Allah, the most gracious, most merciful. As Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your exceptional support to make this channel a grand success. We are a partner and family. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunities into success stories. These success stories can be monetized into value addition. Thank you very much for your precious time. Okay, today I'm going to discuss my lecture number 10. This is my last lecture on smart grid on fax controllers, and my next 5 lecture will be HVDC control system. That will be also part of the smart grid. Before my lecture, I used to read a Quranic verse. Qala Rabbi Shrahli Sadri wa Yassarli Amri Wahlal Uqdatam Min Lisani Yafqahu Qawli Allahumma Rabbi Zidni Ilma. Okay, now on my next slide, I will pay my special gratitude to my professors, and then I will run a complete trail on my lectures. This is my acknowledgement page. I pay my special gratitude all faculty members, in particularly Professor Dr. R.K. Agarwal, former Director of Center of Sustainable Power Distribution, University of Bath. He was my supervisor. I worked with him more than 12 years. Professor Dr. Abdulati Adris Alaid, a former APRI Senior Technology Manager, California, USA. So he was my mentor and external supervisor. Unfortunately, he passed away in 2016. Almighty Allah bless him, highest place in Jannah. Professor Dr. Muhammad Afzal Haq, Professor Dr. Nad Mohan, Professor Dr. Floram Pamtu, Professor Dr. Muhammad Tajambal, Professor Dr. B.S. Chaudhary, Professor Dr. Nasir E. Mahdi, Professor Dr. Akhtar Kalam, Head of Smart Technology from Victoria University, Australia, Professor Dr. Suhail Aftab Qureshi, former Dean UT Lahore, Professor Dr. D.P. Kotari, Professor Dr. Abdul Jabbar, CO ADP, Pakistan. Okay, now we are going to discuss my lecture number 10. Key takeaway points. Earlier we have discussed already completed TCSC functionality, TC operation characteristic, fundamental voltage source converters, voltage source converters, and we have discussed building blocks of transmission network in lecture number 9, state of the art technology, relieving the major bottlenecks, shunt and series compensation response time. Please explore, and you can see lecture number 1 to 9 are complete detail what we have discussed so far. So on my next lecture, I will give you 100 lecture plan, and then I will run a key takeaway points and complete a trail on my lecture number 10. Okay, this is my 100 lecture plan. So during my 100 lecture, we will discuss fax technology concept, power semiconductor devices, voltage source converters, self and line commutated current source converters, SVC and STATCOM operations, static series compensators, static voltage and phase angle regulators, combined compensator UPFC, special purposes fax devices, and application example. I will give you a couple of example fax devices already implemented in United States of America. So what we need to understand fax concept and technology. What is delivery? First, we will describe shaping the global energy delivery, faxed on resolving a gridlock or stalemate of the power system, and delivering a clean and poor power energy. That will be the ultimate goal of when we have complete our 100 lecture. We will witness the following outputs of key takeaway points lecture number 10. Okay, we'll key takeaway points lecture number 10 here. So we will discuss first shunt and power compensation response time. Converter based technology provides a fast and transient free voltage and current characteristic thyristor and converter based technology and loss, thyristor and converter based technology cost factors. Okay, this page dedicated to faculty member and student, in particularly leadership and department chairs, dean and VCs of universities as listed below. University of Engineering Technology, Lahore, Pakistan; NFC University of Chemical Engineering, Multan, Pakistan; RCT Gujranwala, Mehran University, Jamshoroo; NED Karachi, Habib University, Karachi; University of South Asia, Lahore; National University Engineering Technology, NUST, Islamabad; International Research, Islamabad; Karachi Electric; IPFC Qatar sections; University of District Columbia, USA; University of Texas, Arlington, Dallas, Fort Worth, USA; Texas Tech University, Lubbock; University of Bath; Qatar University, Qatar; Texas A&M University, Qatar campus; University of Granada, Spain; University of Salamanca, Spain; COMSATS, Abbottabad, Pakistan; and City University, Peshawar. As I've discussed in my earlier lecture number 9, a New York case study, massive convertible static compensators, STATCOM, we have. And this picture is dedicated to Dr. Abdullah. So if we can see here, so this is STATCOM convertible implemented, leaving up major transmission bottlenecks, strong dynamic voltage support at Mercy. So to increase the transmission capacity 200 megawatt, so the 200 megawatt is sufficient for 200,000 homes. So what we have introduced controllability and flexibility in transmission grid blocks by implementing STATCOM. Okay, this is very important slide to address the time-based contingencies. Okay, first generation is circuit breaker based, second is a thyristor, and third is a converter based. Okay, breaker based is used by the mechanical switched capacitor reactors, and in thyristor based we use thyristors, control protection, transformer, capacitor and reactors, and the STATCOM, GTO, IGBT, control protections and transformer, that is the different configuration each device has. Okay. As we see, STATCOM comparison time response. If you can see here, so the SVC, thyristor based switch devices, and this is my converter based devices. The SVCC normally operate within 2 to 3 cycles, and STATCOM operate 1 to 2 cycles. So both have different configuration: thyristor switches, control protection, transfer capacitor reactors, and here we use IGBT, control protection, transfer and DC capacitors. So that is how they both are responding. In next slide we will demonstrate the compensator factor or I and V characteristic, how the SVC and STATCOM are functioning. Converter based technology provides fast and transient free V and Q control. If you see here in first here, this is my primary voltage A phase, and second here the STATCOM output current at phase A, and third waveform you can see here, before it was inductor mode of operation, it turned into a capacitor mode of operations when there's a transient happen. If you can see here in a primary A, there is some deviation happen on this area, and the STATCOM diagnostic, and it immediately turned from inductor mode of operation to capacitor mode of operation, and there is some variation in STATCOM output current here. So it immediately addressed the issue on this area, but it did not demonstrate that there is any transient. So the converter based technology provides fast and transient free voltage and power control. Okay, now we are going to discuss VIQ characteristic, thyristor based versus converter based for dynamic reactive power compensations. If you can see here, this is my thyristors based SVC, and this is my converter based STATCOM. It will take compensated 2 to 3 cycles, and the second is take 1 to 2 cycles. Okay, this is my V and I curve for the SVC, and this is a curve on my STATCOM. Okay, STATCOM is essentially an alternative providing a voltage support behind a coupling reactance with the corresponding V and I. This is my coupling transformer and providing V and I, respectively both sides here. Okay. The STATCOM can be operated over its full output current range even at very low, theoretically typically about 0.2 per unit value. In other words, the maximum capacitor or inductive output current of the STATCOM can be maintained independently of the AC system, and maximum VAR generation or absorption change linearly with the AC system voltage. So it can go a full capacitive and full inductive mode of operations. So this one is a full capacitive mode of operations, and this is the middle side here, and left side it will go capacitive mode of operation, and right side it will go to inductive mode of operation. Similarly, the SVC, left side will go to capacitive mode of operation and right side will go to inductive mode of operation. Okay. In other words, the STATCOM, the SVC, being composed of thyristor, switch capacitor and reactor, becomes a fixed capacitive admittance at full output. That is the main difference. Eventually, the maximum attainable compensating current of SVC decreases linearly with the AC system voltage, and the maximum VAR output decreases with the square of this voltage. Okay. The STATCOM is therefore superior to SVC in providing voltage support under a large system disturbances, during which the voltage exclusion would be well outside of the linear operating range of the compensator. The capability of providing a maximum compensating current at reduced system voltage enables the STATCOM to perform in a variety of applications the same dynamic compensation as the SVC considerably higher rating. So that is very important, that we need to understand that the STATCOM is more versatile compensator compared to the SVC. Okay, now we have a few highlights on characteristic thyristor base versus what we get again. So as we have discussed here, so the first thyristor based technology, thyristor switch and control capacitor reactor, it has limited performance, limited functionality and large footprint. Compared to voltage source converters technology, converter based is superior performance, versatile functionality and small footprint. That is three main key elements which make the difference between V and I characteristic compared to the SVC and STATCOM. Okay, second here, so the thyristor switch are large footprints, and it's very important here, and this is a smaller footprint, 3 to 40% smaller than compared to the SVC. Okay, now this is the cost factor. This is very important slide again. Thyristor based versus converter based controller cost structure here. So we are going to give you a breakdown here. So if you can see on the left hand side, 20% is the solid state devices, cost and magnetic 12%, and auxiliary component 6%, passive component 20%, and field construction 42%. So the SVC, as we mentioned, the large footprint and field construction required 42% cost. If you come on the other side, so the converter based, so the major cost is the solid state devices, and 20% is magnetic devices, magnetic components, auxiliary components 8%, passive components 2%, and 20% field constructions. Okay, so now the overall cost factor, the low cost, limited a performance, a single functionality, this is the SRV demonstrate, and STATCOM will demonstrate a high cost, a better performance, versatility, functionality 25%. So the SVC and STATCOM, the STATCOM is 20% more expensive compared to SVC, so therefore, so the high cost, better performance, versatile functionality. So we would prefer to have definitely 25% more cost but better performance and versatility functionality. Okay, converter based technology function as zero inertia synchronous compensator. Okay, if we can see here, we are using a two compensator here. One is a rotating compensator and other is a static synchronous compensator here. In rotating compensator, this is my transmission line V voltage and this is my E from the exciter outlet voltage. Okay, so the deviation between V and E, I will respond accordingly. Sometimes it will go into the capacitive mode of operation and inductive mode of operations. Okay, so now this is my X here, the machine circuits reactance bus transformer leakage inductance. Okay, how are we calculating I mode of operations, capacitive inductive mode of operation? If we can see here, I is equal to V minus E divided by X. So that is the reactance. So divided by reactance, it will be equal to I. So if E is greater than V, then I will be the capacitive. If E is less than a V, then I will be inductive. If E is equal to V, then there will be no flow I through the line here. So that is important, we need to understand. Similarly, on static synchronous compensator, this is my transmission line voltage and this is my converter outlet voltage. Okay, this is my I as we have shown in rotating compensator. This is the I how we calculated, V minus V0 divided by X. So that will be I. So if V0 is greater than V, then it will be I will flow in capacitive mode of operation. If V is less than V, then it will be inductive mode of operation. If V is equal to I, then there will be no flow of the current here. So this is the transfer leakage inductance. So this is the static synchronous compensator and static synchronous compensator, how they are operating parallel to each others. Okay, now we have discussed first we have discussed shunt reactive power compensator response, converter based technology provided at the fast free of transient, voltage VI, voltage and current characteristic thyristor based versus converter based dynamic reactive power compensation, thyristor and converter based cost factors. So we have discussed of 4 factors. On our next 5 lecture, we are going to discuss HVDC control and operation. Thank you very much for your precious time. Okay, these are references, the paper which I have published in different conferences and journals. Thank you very much for your precious time. Together, everyone achieve more. Please don't hesitate, send me your feedback and comments t.masood.dr@bath.edu. Please stay at home, safe, inspired and blessed. Thank you very much again for your precious time.